Hey guys, hope you are or had a good break. I guess I'm doing this on break right now, so I am having a good break right away. So we're going to get into this last unit for this semester, and it's all about electrons. All right, we're going to start with something familiar with Bohr models, and then we're going to transition to some math associated with figuring out energies of them. Um, and then that's going to transition into completely new topics on atoms that you've never done before, which is why I think this is the start of kind of some fun chemistry, just because it's different and it's new and you've never had to deal with these before, so you have to think and grow a little bit. All right, so we're going to get into it, and then we'll talk about it a little bit more tomorrow. So make sure you take some good notes on this. Remember, you don't have to write down everything. Just write down the most important stuff, and we'll back it up later. All right, so like I said, we're taking a look at Bohr's model, and Bohr used hydrogen because it was simple, right? It's only got one electron, one proton, and really he was just looking at those electrons and what they did. And what he found out was two things. He found out that electrons orbit, right? They orbit in what he called, or what is known to be, energy levels. And so that's what these rings around it really are. They're really not these set paths as he thought it, but they're energy levels. They're spots where electrons can hover, can orbit, because of their charge versus the nucleus charge, right? And so this is a gross misdemeanor of sizes, but it gives you the general sense of what's going on. But a proton's charge, even though it looks huge here, and electron's charge are balanced. They're kind of the same thing, right? But the proton or electrons are moving really fast, so we got to kind of counteract that. So they orbit in those levels, and electrons, they can't be in between these levels, right? So they can travel in between, but they can't stay there, right? So that you're never going to find an electron in this area. That's what Bohr said. And so they can be in energy level 1 or energy level 2, or we go all the way up to energy level 7. All right. And those electrons, when they travel, which they do as we build them, is fine. But remember, we talked about this before as being like a ladder. Like you can step here and you can step there. You can move your foot in between there. But if you try to get any stability in between, it's not going to work. And electrons do the same thing. All right, so let's get a little bit deeper into Bohr. And we can see some models right here of calcium and radon. And those have, fairly simple to, really complex. And what we see right here is one of the rules that Bohr came up with is each energy level can only hold a certain number of electrons. Okay, each energy level can only hold a certain number of electrons. So when we look here, we can kind of see that pattern starting out. And one shows it just kind of separate all around, and what we're going to find out is they kind of group up into pairs, so that's why we kind of look at them. In Bohr's model, it doesn't matter. As long as we get the right number at the right level, we're good to go. All right, and so when you look at this, if you look at both of these models, level 1, right, is that first ring, the lowest amount of energy, and it always has 2 electrons, right? And so that's what we'd want to put there is 2 electrons. Levels 2 and 3, depending on which one of these models we look at, and depending on what we think level 3 to be, they can be different numbers. So if we look at this one, here's level 2, and it's got 8. Here's level 3, and it's got 8. If we go over to this atom, level 2 has 8, so that's good. But then when we go to this level 3, we see it has, right? It has more. And what's the deal with that? Well, all of a sudden we start bringing in these red ones, right? And we gotta consider that. We got to talk about that and what that means. All right. But for us, what we're going to consider, we're going to think more on this model, because this is really what Bohr intended. And so the first and third, or the first has 2, the second and third have 8. And then once we get beyond that, then we start looking at this model, which really truly isn't Bohr's model, because he didn't understand what was going on with some of those transition metals, right? And so we have 18 and then 32, depending on how big we go up. And we could count those, but basically 4 and 5 were said to have 18, and then 6 and 7 could have up to 32. All right. And the reason we want to know that is for the second rule, right? Each energy level must be filled before we get to the next energy level, right? So we got to fill energy level 1 to get to 2, and then we got to fill 2 to get to 3, and so on and so forth. All right. So we'll try that right here. So we're going to draw a couple of these Bohr models, and I'm going to bring this up. So we're going to do oxygen 16. Remember, that's just the mass, so it doesn't matter. And then we're going to do chlorine 37. All right, so what we got to know for that is just the number of electrons. So if I take a look at oxygen, 16, what I need to remember is oxygen has, look at your periodic table, it has 8 protons, which means it's got 8 electrons. So sometimes I like to just put a plus 8 in the middle just so I remember, right? And then we can go and I'm going to put electrons. So I like using little e's, or you can use dots or whatever. So I put 2 there, and now my energy level 1 is filled up, because what we looked at before is energy level 1 can hold 2 electrons. Energy level 2 can hold 8 electrons. Energy level 3 can hold 8 electrons. Energy level 4 can hold 18 electrons, depending on what we're looking at. So I have my energy level 1 done. All right. And so I'm going to go on to my energy level 2. And here I can hold up to 8. But I already have 2. And on this one, I only need a total of 8 electrons because it's got 8 protons. So I can just start filling it up. And that tells me I need, right, 6 more. Again, you've done this before. You're probably fairly good at it. Okay. The next one we talked about was chlorine 37. Now, again, it doesn't remember. The biggest thing is we got to take a look at, all right, chlorine has 17 protons. Okay, 17 protons. So I'm going to take those and I'm going to start building it up. Okay, I'm going to put in my electrons right there, make them a little bit bigger. I'm going to go to my next energy level. And remember, energy level 2 can hold 8. So if I fill all these guys up, I end up at 10, right? So I'm going to pair them up because it's easier to count that way. So I get 8 right here, and I'm at energy level 10. Okay, I'll go to my last one in this case, because right now I'm at 10, and I know this is going to be my last because level 3 can hold up to 8, and I only really need 7 more because I've already filled out 10. So I'm just going to put those in. All right, doesn't really matter where you put them. I'll just pair them up so it's a little bit easier to count. And right there, we've just done our next Bohr model, right? So I'll have you try a couple of those in class tomorrow live. But if you understand that, those should be no problem. We'll talk a little bit more detailed about them. All right, so those are our 2 Bohr models. All right, so that's great now, and we're going to try to figure out what that means, what that is telling us. All right, and so we got to think about this idea of light, right, and how really Bohr came to his idea. Okay, and so we know light as a wave, right? We've always talked about it in all of your years of science. You thought of light as a wave, and we call that electromagnetic radiation. We'll take a look at that chart in a second, right? And so Bohr used that idea to make his models, like we kind of talked about before. And what he found is that at certain energy levels of light, he could make the electrons move. And so that's what he did with this hydrogen atom, right? He shot different amounts of energy at it, and he would find, even though it only has 1 electron, so it should just be at that first level, he was able to shoot it with different amounts of energy. And he found that, hey, with this amount of energy, it would circle at this level. And he kept on able to build it out. Right? So that's kind of what he was doing with it. And there's more that we're going to talk about that when we get there a little bit deeper. And this can be used, and it can be used to calculate the amounts of energy. So we have 2 different equations, and we're going to break both these down. All right, so we have C equals nu times lambda, and we have E equals H times nu. All right, and we're going to take a look at each one of those as we go along. Right, let's see. So we have our functions of electromagnetic spectrum, and you can just take a quick look at this. But we have wavelength up here, and kind of what these numbers mean. They're in meters, and you can see, 10 to the third all the way down over here to 10 to the negative second, and you can kind of see what they look like. So we have radio waves and microwaves and infrared, and over here we have visible and ultraviolet, and the size of football fields all the way down to size of molecules or as big as an atom down there. And then we have frequency down here, and we have energy at the bottom. So we're going to take a look at this together. There's nothing that you need to remember or know on here, but it's just kind of it's a nice way to kind of quantify what it is that we're talking about. Okay, so let's look at our first real equation. So we're taking a look at the speed of light. Okay, and you might have seen this equation before, but it's C equals V times that upside down Y looking thing, right? So we'll take a look at what each of those are. So C is the speed of light, all right? And the speed of light is always 3.0 times 10 to the 8th meters per second. We'll get that in a little bit, but 3.0 times 10 to the 8th meters per second, okay? So that's a constant. Light doesn't change unless we pass it through a medium. That V, that is actually the Greek letter nu, which stands for frequency. And frequency is a hertz, right? That's its unit, but hertz doesn't help us as much as we think it does, especially mathematically right now. So if you think of a hertz as 1 over a second, or like a wave per second, that's what a frequency is. So as you're looking at, the waves coming in an ocean, right? If you get one wave hitting the shore every second, the frequency of those waves would be 1 hertz. If you get 2 per second, all right, then you'd have 2 hertz, and so on and so forth. And the last one, the upside down Y looking thing, is lambda, and that's our symbol for wavelength in this equation. And wavelength is, excuse me, measured in meters, and we want to remember this, right? So this is something that we may need to use in the future. So 1 meter is equal to 10 to the 9th nanometers, because we're working with really small units, and so sometimes we'll get this nanometers out there, and we can just do that conversion pretty simply. And so when we look at this, we can look at 2 different waves like this, and this one would have a long wavelength, right? This one would have a short wavelength. This one would have a very fast frequency, right? Because there's more waves per second, and this one would have a very low frequency. So whether we visualize the waves or we calculate them, that's really what we're trying to do. Okay, so let's take a look at one problem. So it says, what is the wavelength of light that has a frequency of 571 times 10 to the 14th hertz? All right, so let's take care of that first. We're going to bring down our visualizer again. All right, so 5.71 times 10 to the 14th hertz. All right, so let's bring down this guy. We'll take a look. All right, and we'll do a calculation. All right, so what we know is we have a known, right? So we have 5.71 times 10 to the 14th hertz. Now, I know hertz is frequency, right? So that's my nu. We only have one equation so far, and so on this one, I know I'm going to use the equation C equals lambda times nu. Okay, and it asks us to find that guy right there, right? We want to know what is the wavelength of this guy, knowing we have the frequency. All right, so my wavelength is going to be my unknown. All right, and that should be measured in meters, so you might want to take note of that. And then I wasn't given C in my problem, but like I said, we're going to write this down. This is something that you want to remember and write in your notes. This is 3.00 times 10 to the 8th, and this is in meters per second. Okay, again, so most of chemistry, at least as we're doing it, comes down to pretty simple algebra, and that's what we want to do. So we're trying to find lambda, right? So I'm going to rearrange this guy, and so I know that lambda is equal to C over nu. All right, if I put in my numbers, I have my 3.00 times 10 to the 8th meters per second, and I have my 5.71 times 10 to the 14th hertz, right? Now this is where hertz kind of gets us a little bit lost. So really remember, hertz is a per second, and so what that does officially is it takes out our seconds on both top and bottom, and so we're left with meters, which is good because that's exactly what we were trying to find. Right, so now we can toss this into our calculator, and let's see what we come up with. So we have 3, turn it on. We have 3 times 10 to the 8th, and that's going to be divided, use parentheses, 5.71 times 10 to the 14th. And I come up with an answer of 5.25 with 3 sig figs, right? So I have 5.25 times 10 to the negative 7th, and my unit in this case would be meters. All right. There we go. So take a look at that, copy that down, because you'll have to do a couple problems like that, but I'm pretty sure you guys can be pretty good. So let's go look at the last little bit. What color would that be, right? And so when we get this chart to come in, the nice part about this is we can take a look. We just calculated that we have 5.25 times 10 to the negative 7th meters. Well, if we go back and we do our calculation before, that really turns into 525 nanometers. Okay, so 525 nanometers would get us where on here? 525. All right, so that's somewhere in right here. So what we would say is, if I ask you for this, I'd say, hey, we would be some form of green light. Okay, answering that